video about the intensity of sound waves. These are under conditions of transmission. We are not checking the absorptivity and the sonar reflection either, but it's just about sonar transmission. It can be infrasonic. It's viable for infrasonic and ultrasonic, i.e. all sorts of longitudinal variations. So the first one, so the formula with which you identify it is intensity equals 2 pi squared frequency of sound squared amplitude of sound squared density of the media through which it's being transmitted, and then the velocity of the sound. Now this part is square and these are linear, so this is squared and this is linear, as in like it's singular. It's singular, but this part is square. So 2 pi squared times f squared, which will be in hertz, amplitude will be in meters, this will be in kg per meter square, kg per meter cubed, and this will be in meters per second. So if we do the dimensional analysis, we'll get 2 pi squared times 1/second squared times meter squared times kg per meter cubed times meters per second. Now this should equal watts per meter squared. So we'll get kg per second cubed. If we try to find out the dimensional units of intensity, it'll be power over area, which is resolved as energy over time times area, and then energy is Fx, force times distance over time times area, and then force is mass times gravitational field. The force acceleration due to gravitational field, it'll be m times g times d over t times a. So it'll be kg times meters per second squared times x. So it'll be kg times meters per second squared times meters, and then over time times area. So we can cancel out m and m squared. So we get second and then we can cancel out kgs, so we are left with kg per second cubed, and here kg per second cubed in this formula is consistent with the general dimensional units of intensity. So the intensity's units are kg per second cubed. So the units of intensity in general are kg per second cubed, and here it's also kg per second cubed in a pi radian fashion. So the dimensional units of intensity, so this equation is consistent and is correct because the units of intensity are in line with the linear units of intensity. So it'll be, so the intensity of sound waves is given by this equation, and it's applicable to infrasonic, ultrasonic, and subsonic and hypersonic and all sorts of sonic longitudinal oscillations. And it's about the sonar transmission, not about absorptivity. It's about it's sort of a pre-absorption it carries out measurements for pre-absorption stage, i.e. where it's about to hit the medium. So it only calculates everything prior to the sound waves, the sonar hitting the medium. And it's this formula, which is 2 pi r squared, 2 pi squared f squared amplitude squared times the density of the medium times the velocity of sound, which in air is 330 meters per second. In liquid, it's 1545 or 1550 meters per second, and in solid, it's about 45 or 5,000 meters per second. So that's about, by a factor of 3. So in liquids, it's 330 meters per second. In fluids, it's 1550 meters per second, and it's in solids, it's approximated to be uh, sorry, that's meters per second. So 330 meters per second for air, 1550 for liquid fluids, water, seawater, and 5,000 for concrete and walls and what have you. So we know that intensity is kgs per second cube. So that's good. Thank you very much for giving your attention to learning about the intensity of sound waves in a pre-absorption scenario. And I'll take it from here. Thank you very much.